So continuing with the topic of integration methods, the first integration method is U-Substitution. So previously, in the intro to integration methods video, we said that there's U-Substitution for indefinite integrals, and there's U-Substitution for definite integrals. So for indefinite integrals, there we are not evaluating anything, we're just trying to find a general antiderivative. But for definite integrals, we're trying to actually find a specific area under a curve. So there's going to be bounds, there's going to be an upper limit and a lower limit. So starting off with the general formula for indefinite U-substitution. So say we are taking the integral of a composite function such as f of x, f of g of x, f of g of x times g prime of x, right? This is the U-substitution actually takes into account the chain rule, right? It undoes the chain rule, so let's write that here. Undoes or undoes, whatever, the chain rule. So this should be equal to basically f of u du. So what we're simply saying, there should be a dx here too. So what we're basically saying is that this composite function can be changed into this f of u du, which is a lot more simpler. And we can do that by making g of x equal to u. So u is equal to g of x. We can make u equal to g of x, and we get g prime of x. So in order to switch basically the variables, since we're right here, we're in variables of x, and we're trying to switch to variables of u, we want to make sure everything switches to variable of u. So if we switch g of x to u, we want to make sure this entire differential also switches to u. And we can just do that by taking the derivative here. So du dx is equal to g prime of x. So I just took the derivative of this. Now we want to switch to the variables of u, right? That means that we want to actually multiply this dx on both sides, and we get du is equal to g prime of x dx. And if you look back at the basically setup of the indefinite U-substitution, we see a g prime of x dx right here, and we know it's equal to du, and we can just write du there, and we end up with this. So in this case, we're going the result of indefinite U-substitution. So let's write result is a general antiderivative. Derivative of the function, or the function. But for definite for definite integrals, we're gonna actually get an area, a whole area underneath the curve. So let's go on to definite. So the result of definite is an area under a curve. So the general formula for definite integrals is basically similar to indefinite. However, we have bounds here, a to b. It could be any bound. However, just for this general formula, it's going to be a and b, a to b. And when we do this, once again, we want to switch everything to in terms of u, right? So we can do the same thing as indefinite, right? So f of u du, and it's the same process here, right? But in this case, we have bounds. We have bounds that were associated with the term x, the variable x. So we want to make sure we switch these these bounds to terms of u. So we want to switch these bounds. So let's just write switch bounds to terms of u. And when I mean in terms of u, so in terms of u. So when I say in terms of u, that I'm basically saying that evaluate the bounds, evaluate the bonds with whatever you substitute for u. So we're going to be substituting u for g of x, right? So we know that u is equal to g of x. We want to evaluate each of these bounds. We want to evaluate a at g of x, and then we want to evaluate b at g of x, and then use those bounds as in our final setup. So we're basically saying we want to evaluate g of a, we want to evaluate g of b, and when we get that, we are in terms of u, because u is equal to g of x. So we want to do g of a, g of b, and once you do that, once you do this, you can actually evaluate regularly, just like how you would solve an indefinite integral using the fundamental theorem of calculus. So all you would this would basically just be f of whatever that was, g of b, minus f of g of a. So g of b and g of a are just the bounds switched to in terms of u, and then you evaluate regularly using the fundamental theorem of calculus. So let's do a couple of examples that involve U-substitution. We're not gonna do the indefinite U-substitution. That's the definite U-substitution takes into account all of this whole process. So I'm just gonna go straight to definite U-substitution. So let's do that. So right here, example. So we have the integral, the integral from 0 to 1 of x cubed over radical 1 plus x to the 4th dx. So we're going to be using U-substitution, and this is a definite integral since this has bounds, right? It has a lower bound, it has an upper bound. And we're going to use this general formula right here that we already explained. So first thing first, we want to actually determine what is u. What are we going to plug in for u? And we can do that by looking at whatever is inside of parentheses or under a root. So we see that 1 plus x to the 4th is under a root. And we know that we're gonna need du. That means that we're gonna need a derivative that's gonna help us basically turn this dx into du. So let's say u is equal to 1 plus x to the fourth. All right, so 1 plus x to the fourth, and we know we want to change the terms of x in terms of u. So what we're gonna do is take the derivative here. Du dx is equal to 4x cubed d 4x cubed, just 4x cubed. Now we want it in terms of du, so du is equal to 4x cubed dx. So we know that if we want du here, if you want to use 1 plus x4 as u, we need a 4x cubed dx, so we can switch to du. So we look back at the original function, and we see that in the original function we have a dx, so we're good with the dx. We have an x cubed here, right here. We have an x cubed, but we don't have a 4. So we don't have a 4. And the good thing about U-substitution is we can actually add in 4s, and as long as we cancel it by putting its reciprocal outside of the integral. So let's do that right now. So say this is the integral 0 to 1 . Let me rewrite this a little better. So 1 over radical 1 plus x to the fourth times x cubed dx, right? This is the same thing as this. I'm just rewriting it. So say we need a 4x cubed, right? We need a 4x cubed. So just add a 4. Just add a 4 here. But since we added a 4 here, we want to make sure this 4 cancels in the end product. So what we just do is put a 1/4, or in other words the reciprocal of 4, outside of the integral, like that. And then we just say 1/4 0 1. So we know this is gonna be u. 1 plus x4 is u, so radical u. And then we know this entire expression is just du, right? Because we calculated right here. So this is going to be du. Now that we have this, now we can evaluate like any other definite integral. So first thing we're going to do is actually solve for the general integral of this expression 1 over radical u. So let's actually do that. Let's do this to the side right here. So the 1 over radical u du that's going to be simply u to the negative 1/2 du. And then when we evaluate the integral, all you have to do is just add 1 plus 1, negative 1/2 plus 1, and we get 2 u to the 1/2, or in other words 2 radical u. That's what we get. So that's for the indefinite integral part, right? But there's one more thing. We have to evaluate these bounds in terms of u. So let's actually erase these bounds here and evaluate these bounds at u. So we know u is 1 plus x to the fourth, right? So let's do that. So so we want u of, where was it? 0. So let's take f of 0, and then let's take f of 1. And this is just a function u is equal to 1 plus x to the 4th, right? We're going to evaluate at this function. So f of 0, so we're just going to say this is f of x for changing the bounds. So 1 plus 0 to the 4th is just 1. 1 plus 1 to the 4th is just 2. So our new bounds are 1 to 2 when we switch in terms of u. So once we get to that, now that we have our bounds changed, now that we have our indefinite integral that we needed, now we can just start evaluating. So I'll come all the way down here, bring this all down here. So we are left with 1/4 1 to so we know that indefinite integral is basically this right here. So we can write 2 radical u. We know the bounds, the new bounds are 1 to 2. We can simplify, actually first we're not going to simplify just yet. We're going to evaluate this separately and then multiply this 1/4 at the end. So let's evaluate 2 radical u from 1 to 2. So I'm going to pull this to the side. So let's evaluate that. So it's upper bound minus lower bound, right? So we're going to do 2 radical 2, right? We're plugging in 2 for u, minus 2 radical 1. So we're plugging in 1 for u. And our answer for this, so 2 radical 2 is just 2 radical 2. You can't simplify that anymore. And then 2 times radical 1. Radical 1 is just a 1, so 2 times 1 is just 2. So minus 2. So what we get is 2 radical 2 minus 2, right? For this section of the expression, I guess. So what we can do now is plug that in here. So 1/4 times 2 radical 2 minus 2, right? That's what we determined. Minus 2. Now, all we really need to do is just basic algebra with the distributive property. So it's going to be 2 radical 2 over 4 minus 2 over 4, right? Now we can simplify, and we get radical 2 over 2 minus 1/2. So you leave the answer like this, or if you want, you can put all of this over one denominator. So you see that it's one denominator, it's the same denominator too. You can just put everything over one denominator like that, radical 2 minus 1. This is also an acceptable answer. But this is the final answer right here. So what this represents is basically the area of this function evaluated from 0 to 1. So that's what this area represents. So even if we do U-substitution, we're gonna get the same answer. So even if we just switched everything back to terms of x, so say first we did U-substitution, but then at this point right here we switched back to x. So say if we switch back to x, we would just be evaluating this 1 plus x to the 4th So we would just evaluate this if we switched back to x. But either way it would give us the same answer. But since you've already switched to u, you might as well just keep on computing the rest of the definite integral with u. Because if you switch back to x and say you have a very complicated problem, it's just going to get very confusing. So what I would recommend is just once you switch to u, just keep running, just keep the rest of the problem consistent with u, instead of just switching back to x. There's going to be some cases we're going to have to switch back to x, but for most cases you're just going to keep u and just evaluate with u.